that she gave us, so that means that we just it just means all. The ones that make your mother
All right, have we had our sweet fill for the day?
Yes.
Okay. We're going to finish this section today, and it's not going to take us that long to do it because we just have some like terminology to get used to, and then we just have a few examples to go over, but they're not going to be that bad, I promise. So this last part of this section, we're going to talk about vectors. Up to this point, we've been doing parametrics, where we have an x equation and a y equation, but we can use parametric equations to help us define vectors. And I think yesterday some of you said you've heard of them before, maybe some of you have used them before, these vectors, but we're going to take our time to kind of get used to them. They're not going to be too intense because the vectors that we cover in this class are going to be related to position equations. Remember, like position, velocity, acceleration. That's as far as we're going to get into it. So before we go over this kind of reference page here, I just want to kind of recap. Remember the parametric graph we started with looks something like that, okay? And we had some type of x equation and some type of y equation. Parametric equations are nice because they give us a way to graph a shape or a path that's not a function. You notice how it doesn't pass the vertical line test? So these parametric equations, we don't really call them functions like we do other equations we've dealt with up to this point. So what we can do is if this is the path of a particle, we can use vectors to describe its position, its velocity, and its acceleration at different points on this path. For instance, maybe a particle or an object starts here and ends here, and we know it traveled along this path. But what we can do with these x equations and y equations is utilize vectors to describe how it moved or how it changed. For instance, the x equation defines its horizontal position. So if it starts here and ends here, we had some x vector or change that went this way, and we had some y vector or change that went that way. Bless you. Bless you. Okay? So if it starts here and ends here, it had some horizontal change and some vertical change, even though it traveled along this path. Okay? Now notice how when you use vectors in this sense, because we're only looking at left and right and up and down, if we were to kind of draw in the hypotenuse of this triangle, what would this hypotenuse represent? Can you give a name? Displacement. How far you are from where you started. Okay, where it ended, where it started, this is the distance, how far you are. So that's kind of your displacement. Could we figure out the displacement? If we knew the x change and the y change, how could you figure out the hypotenuse of a right triangle? Pythagorean theorem, exactly. Okay, now in terms of calculus, if we were to take the derivative of the x change, maybe I'll draw this down here. If we were to take the derivative of the x change, that would be dx over dt. Okay, we did that yesterday. If we did the derivative of the y change, that would be dy over dt. And what would the hypotenuse represent in that case? Think about particle motion. Velocity. This is how much it, basically kind of the speed to the right. This is its speed up. And if you were to connect those, that would kind of be its overall velocity or speed. So this would be v of t, whereas this one was displacement. Okay, so vectors are just a way for us to separately label some horizontal distance or horizontal rate. We could do a vertical distance or a vertical rate, and by analyzing the Pythagorean theorem, we could possibly figure out displacement and speed or velocity. Okay, So we're not going to, that's basically as far as we're going to get. We're not going to talk about, what are they called, like normal vectors or dot product vectors or scalar multiplication. Some of you may have heard of those before, but we're not going to get into all those different operations. So in terms of kind of notation, we could symbolize the derivative of the x equation as x prime or dx over dt. Again, if it's a derivative, it's a rate. So this would be the rate at which the x coordinate is changing. Same thing with y. The derivative of y would be the rate at which the y coordinate is changing. Now, in terms of vectors, we have these particular ways we could represent them. I know it might be hard to see, but that little symbol over the S is kind of an arrow with just a half of a arrow stem on it. Same thing with the V and the A. That's just a symbol to denote vector. So the position vector we can label as the x position, comma the y position, and sometimes you'll see it written in parentheses. Other times you might see it written in these chevrons. They're kind of like very wide arrows or brackets. We can represent the velocity vector, aka the derivative of position, as x prime comma y prime. And then we know acceleration is the second derivative of position, so that would be x double prime y double prime. Okay, you see the connection with the vectors the same way as they are with regular position functions. The derivative of position's velocity, derivative of velocity's acceleration. Still the same thing going on here. All right, so yesterday we talked about how we can figure out dy over dx, which is like the overall rate, and we would have to take the y derivative over the x derivative. So this is the overall rate of change in terms of your slope. So you'd be looking at a tangent line in that aspect. And we know the second derivative is the rate of change of that slope, where we're kind of referencing concavity. All right, so I don't think any of that is too new for us. What might be new are these last two bullet points. So notice how in this second triangle we drew, we said that the velocity of a particle could be represented by the hypotenuse of the two component vectors, the x component vector, or the derivative of x component vector and the derivative of y component vector. And very similar up here, we said we could figure out the hypotenuse by utilizing the Pythagorean theorem. So notice how this velocity equation is simply the Pythagorean theorem solved for velocity. You have this a derivative plus this b derivative squared, and if you were to square root to get the c or the velocity all by itself, it would look like this. So I don't want you to look at this and get too overwhelmed. It's essentially the Pythagorean theorem solved for velocity. So we're going to utilize that to help us reference or solve any type of speed question. Okay, the speed or velocity of a particle. What if you integrate velocity or speed? What does that represent? Remember from Calc 1? If you integrate velocity, distance, okay, displacement, okay, and this was like the length of the arc from yesterday, right? We wrote that down. The integral from a to b of the square root of the separate derivatives squared being added together. Okay, that was the length of the arc, or the distance you've traveled. So in this graphical example up top, if we were to evaluate that integral from beginning point to ending point, it would tell us the total distance traveled. Okay, even though we were analyzing, this would be displacement, whereas this would be total distance. All right, so we can integrate velocity to get that total distance. That's basically what that's saying there again. Okay, so kind of reiterating myself. So I don't think that this is going to be too difficult for us because the particle motion that we're used to is still related to vectors. It's just the big thing with vectors is you're going to have to write two separate things. You're going to have to write an x amount or derivative or a y amount or derivative, depending on the case. So it's kind of going to look like an ordered pair, where you have one piece, comma, another piece. And we'll check that out as we go through some examples. Okay, so let's go ahead and try example 8. A particle moves in the xy plane. The position of the particle is given by this parametric set. So the difference between this information and Calc 1 information, we would have been given a position equation in Calc 1, but now we're given a parametric set in Calc 2. They're defining the x and y variables or locations separately. So let's try part A. Find the velocity vector at time 1. We'll start with baby steps. If they give us the position functions, okay, one for x, one for y, how do you think we can figure out the velocity functions for x and y? How is velocity related to position? It's the derivative. All right, so let's figure out the derivative of x and the derivative of y. We can do that without a calculator. All right. And they want us to figure out the velocity vector at 1. So if you were to plug in 1 in for the t's in the x derivative, it looks like we would get 11. And if we were to plug in 1 into the t's for the y derivative, looks like we would get 1. So the 11 is representing our rate of change horizontally. The 1 is representing our rate of change vertically. Let's go ahead and represent the velocity vector. So we would say v of t, and we would have that little half arrow above it, symbolizing a vector. And this is going to look like an ordered pair. You can use parentheses or those wide arrows, those chevrons. And then kind of like an ordered pair, it normally goes x, y. We'll put the rate of x change first and the rate of y change second. That's our velocity vector. Not too bad. Let's try B. All right, find the speed of the particle at 1. All right, so speed is the absolute value of velocity. All right, so if we were to kind of imagine this in terms of our right triangles, the rate at which x is changing is 11. The rate at which y is changing is 1. We need to figure out the overall velocity if we were to kind of draw a straight line from beginning to end. So we're going to utilize that Pythagorean theorem. So maybe we'll do, let's see, we'll do 11 squared plus 1 squared equals velocity squared. See, this would be 122 equals velocity squared, and then you can square root it. You doing okay? All right, let's check out C. We also then want to find out the acceleration vector at time 1. How can we figure out maybe the acceleration equations, first of all? The second derivative. All right, so we're going to take the second derivative of the x equation, the second derivative of the y equation. We already know the first derivative, so that's nice. I see this would be 6t plus 8, and then 12t squared minus 6t. So if we were to plug in 1, looks we got 14 and 6. So in terms of kind of vector notation, we would need a of t with a little half arrow above it would equal 14 comma 6. Okay, the acceleration horizontally and then the acceleration vertically. Doing okay? Not too bad. It's related to the position functions that we're used to. It's just different notation, which can be a little new or something to get used to. All right, let's try the next one. A particle moves along the xy plane so that we have these parametric equations, or parametric set, and we're only looking from 0 to 2 pi. So they're looking for us to figure out the overall first derivative and then the kind of overall second derivative. How do you want to do that? Of each. Okay, so we'll do, let's see, x prime. The derivative of square root of 3 is 0, so it goes away. Then we need to subtract 4 times the derivative of cosine, which is negative sign, so that would change it from a negative to a plus. The derivative of the y equation, negative 2 cosine t. So if those are the individual derivatives, how can we kind of merge those together to get the overall rate of change? Yep, we're going to take the derivative of y divided by the derivative of x. So negative 2 cosine t over 4 sine t. And can we simplify it? What do you want to do? Negative 1/2. Close. Cotangent, yep. Cotangent t. Perfect. All right. So now we get to the trickier one. How can we find the second derivative of a parametric set? Can you describe it? Okay, so we got to take the derivative of the first derivative, but it's a little more complicated than that. We have to divide it by the x derivative, which we had up here. Okay, so let's think about this. The derivative of cotangent. Not quite. Do we remember the derivative of tangent? Ah, there we go. Secant squared. All right, so can we make an educated guess as to what the derivative of cotangent would be? Negative cosecant squared, yes. So it's kind of the opposite trig function. Instead of secant, it's cosecant, and it actually happens to be negative. Little fun fact, in terms of your trig functions, the derivative of any c trig function is negative. Like the derivative of cosine is negative sine. The derivative of cotangent is negative cosecant squared. So if this is negative 1/2 cotangent, and this is the derivative of cotangent, notice how the negatives would cancel. So we'd have 1/2 cosecant squared x. So that's the derivative of the first derivative, but we got to divide that by the derivative, or the x derivative, which was for sine t. And I didn't mean to put an x there, it should be a t. Can we clean that up? One half divided by 4. That'd be 1/8. And then what about cosecant squared over sine? First of all, do we know what cosecant is? Can we rewrite that somehow? Cosecant? 1 over which trig function? You guys are scaring me a little bit. Cosecant? 1 over? Sine, thank you. All right, so cosecant squared is the same thing as 1 over sine squared. So imagine this, if we have 1 over sine squared divided by sine, instead of dividing by sine, we could bring it up and multiply by the reciprocal, which would be 1 over sine. So we would have 1 over sine cubed, which is the same thing as cosecant cubed. All right, we can simplify it or rewrite it. Good job, guys. All right, so for the same question, let's kind of bring in some of this vector idea, perhaps. The path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate. Remember, this was no calculator, so they just want the setup. If we don't have a calculator to actually perhaps type it in, no big deal. So how can we possibly figure out where, or the time, that the particle intersects the x-axis twice? If you think about an x-intercept, the y value is always 0. Okay, so let's go ahead and take the y equation and set it equal to 0. That should at least give us the time where it intersects the x-axis twice. So subtract 1, divide -2, we'll get a half. And without a calculator, this is where we have to might dig a little deep. Okay, in terms of your unit circle, can we figure out where sine has a value of a half? There we go. Pi over 6 is in the first quadrant. All right, and since sine is like a y value, y values are positive in quadrant 1 and quadrant 2, so the other time would have to be in quadrant 2. Instead of going pi over 6 up on the right axis, we should go pi over 6 up on the left axis. So if you take pi minus pi over 6, that would give you that 5 pi over 6. So we have 2 times. So those will come in handy. All right, so how can we represent the total distance traveled by a particle? If you think about kind of that example from the way beginning of the section, if we start here and end there, how can we figure out the total distance? But we take the integral of it. Right, this is essentially arc length. Okay, the length of a curve. So we'll say total distance is the integral of that Pythagorean theorem. So square root, we need the 2 derivatives squared and then added together. Looks like we know those from part A. So 4 sine of t squared plus, we're running out of room, negative 2 cosine of t squared, dt on the end, and it looks like our bounds would be the times, because we want the distance between both of those x-intercept values, or points. So pi over 6 to 5 pi over 6. We doing okay? Pretty good? Okay. The next section really isn't anything new. It's just more practice with these vectors and getting used to identifying what exactly they're looking for. So we'll just have more practice basically tomorrow and the next day. Okay, nothing too new.